everyone. My name is Sungmin Kim. I'm an associate professor at the School of Electrical Engineering at KAIST. So my talk today will be about recent opportunities in battery-free sensing. So before we move on, I run a Smart and Mobile Systems Lab, or SMART Lab in short. We have 8 PhD students and 2 master students, and we work on mobile computing, including battery-free sensing, Internet of Things, and 5G and 6G systems. So what is mobile computing in the first place? So we build useful services on mobile devices. Our work ranges all the way from hardware to the software, including wireless system integration and wireless communication networking, and lastly, application and services. So what is a battery-free tags? Battery-free tags are simple and small wireless devices that operates without batteries. They often come in the form of stickers and wearables. And without batteries, they operate via energy harvesting using solar cells, RF harvesting, and so on. So why do we need battery-free systems? We have learned that we will face enormous and massive amount of IoT in the future. And with the increasing number of IoTs, which runs on batteries, as the number of IoTs grow, we'll face the problem of Internet of Dead batteries. Meaning that with massive amount of IoTs, we might have to start our days by replacing hundreds and thousands of batteries, which simply doesn't work. So that's where the battery-free sensing kicks in. So the advantage of battery-free sensing is the scalability and deployment and maintenance cost, and it lasts long and is eco-friendly since it does not have a battery. However, the downside is that it has limited power and thus limited operation capabilities, including low quality data and high latency. So my talk is how can we do anything about the bad side to improve it? This talk consists of 2 parts. First part is about improving battery-free sensing using AI. And second, we'll talk about improving battery-free sensing using the new spectrum of millimeter wave. Let's first talk about the AI part. We build extremely low resolution RFID tags equipped with 6 by 10 pixel NIR sensor, powered by solar harvesters only, which achieves 2 FPS under low light conditions without direct light. And this works with commodity RFID reader. The important thing is that 6 by 10 pixels doesn't tell much. As you can see, the screen of the nature, after it's sensed by the NIR sensor, the 6 by 10 pixels doesn't tell much. What this indicates is that we are able to achieve privacy-preserving camera. However, the problem is that it is not quite good for gesture recognition as well. However, by looking at the temporal dynamics, as you can see on the top, the movement can be captured by looking at the pixel difference over time, even in 6 times 10 pixel image. And this movement can be captured by our neural network that is designed to capture fine-grained temporal features as well as spatial features at the same time. With this system, we are able to achieve an average of 93% accuracy over 10 classes, and we are able to track limb level movements. Now let us move on to the next part of improving battery-free sensing using millimeter wave spectrum. This work is on localization, where the key aspects of localization is as follows. First, we want high precision. Second, we want to able to localize many objects. And lastly, we want to localize objects over the wide area. This system, using commodity radar, tracks our battery-free tag, custom built in our lab, which is able to achieve sub-centimeter precision localization and tracks more than 1,000 objects at the same time and over the distance of 180 meters. This comes with the benefit of millimeter wave battery-free tags, where we are able to exploit a very large bandwidth of millimeter wave and a very low power consumption of battery-free tags. In other words, backscatter. The challenge in using millimeter wave spectrum is a very high loss, which is proportional to the square of the frequency. We tackle this problem by using FMCW radar, which is able to translate the large bandwidth of millimeter wave into a large amplitude boost, in other words, high processing gain. By doing so, we are able to address the high signal loss problem, and we are able to achieve very precise localization. In indoor and outdoor, we are able to achieve 180 meters and 80 meters while maintaining our accuracy under 1 centimeter medium localization error. And we are able to track in real time the moving robot. And lastly, we're able to track 100 tags in only 33.2 milliseconds. Let us watch a video on indoor real-time localization. So with that, we're able to realize many mobile services, including smart shopping. For instance, by tagging the items and only by pointing at an item, we're able to pull up more information about that item, like stocks and ratings. Also, we are able to use this in smart factories to track all those machines in the smart factory. And then lastly, we are able to monitor structures, including sinkholes. So with that, I would like to conclude my talk. Thanks for listening. And if you have any questions, please email me. Thank you.